Welcome all of you on this platform of learning. This video is dedicated to all the experiments that we discussed in the chapter Electromagnetism. The very first experiment that we discussed in the chapter was Hans Oersted experiment, which was related to magnetic effect of current. He found out that a current carrying conductor starts behaving like a magnet and hence has a magnetic field around it. So this will be the first experiment. The second experiment that we will be discussing is Lorentz's experiment, on which DC motor works. According to this experiment, an electric current is passed through a conductor placed normally in a magnetic field, and hence a force acts on a conductor, as a result of which the conductor starts to move, and thus a mechanical energy or work is obtained. So we will be working on this experiment as well. The last experiment that we will be working on related to Faraday's experiment, on which AC generator works. And according to this experiment, Faraday found out that when there is a relative motion between a magnet and a solenoid, there is a change in the number of magnetic field lines per unit area, means the magnetic flux. So there is a change in magnetic flux, and hence an induced EMF is produced in the solenoid, which results in induced current. Or indirectly, Faraday concluded that current can be induced with the help of change in magnetic field lines per unit area. So let's work on these experiments. Let's move to our physics lab. It was the first person who actually tried to bridge the gap between electricity and magnetism. He was the first one to work on this. Actually, before that, it was considered that current, electricity and magnetism, they are two different fields. But Oersted, he tried to connect the two concepts, current, electricity and magnetism. And we are now going to show you the experiment that actually changed the whole scenario in 1820, right? So it was, as we know that this is a magnetic needle and it's pointing towards north and south right now, if you see here, right? So this is pointing towards north and south. And this was actually a simple setup was there by Oersted. He was actually working on something. This is a battery and these are simple connector and this is a conductor, right? He was working on this conductor when he suddenly saw that there is a deflection in the magnetic compass. He was very surprised because nearby no other magnet was lying. So he thought of that must be some magnetic thing is lying nearby. That's why this magnetic needle is giving deflection. So he tried to search on, but it was all in vain. Then he again started working on this experiment. Like here, connectors are there. This conductor or the connecting wire is there. Copper wire is there. So if you see here, when it was like this magnetic needle was lying nearby. So when the circuit was complete, there was deflection in the magnetic needle. So I'll just do it again. So can you see that there is a deflection in the magnetic needle? Can you see the deflection? So when it was kept here, deflection was there in the magnetic field. So the moment we bring it near, you can see the swing in this needle. So on this basis, Oersted tried to inform that this current carrying conductor is actually behaving like a magnet. Simple conductor, simple copper wire, it will not be serving as a magnet. But the moment we pass current through it, this current carrying conductor, now though there is an electric field because of the current produced in this conductor, but there is a magnetic field also. And why this magnetic field? Because this current carrying conductor, it starts behaving like a magnet. So to his surprise, if you see here right now, this needle is swinging from north towards south, right? But the moment I keep this magnetic needle on the wire, so let's see what happens. If I just keep this magnetic needle on the wire, what will happen? Again, deflection is there, right? Deflection is there. It's like this. So if you can see here, now the swing is moving towards northwest. Can you see? I think I have given a swing here. Yes, now from south to west, north to east, swing is increasing. And if I keep it like this, what happens? See here, right? So this was an experiment that revolutionized everything, and that made a connection between current and magnetism. So is it going to happen if I keep it this way? I'll not be able to give demo on this, but yes, now it is actually showing east and west. Like here when we were having, it was showing me north and south. Now it is deflecting from east towards north. But the moment I keep it other way, if I just change the direction, the deflection also reverses. Now let's check what happens if I change the terminals. Okay, so let's see. If I change the terminals, what will happen? Now it is, can you see? The direction is actually reversing. It is now moving from east towards north, right? It was before north towards east, but now because I have changed the terminals, that's why the direction of current has changed. And that's why, because direction of current has changed, that's why polarity has also changed. With the result, the deflection in this magnetic compass has also changed. Fine? That's all regarding OERSTED'S experiment. So this is set up for your Lorentz experiment. So if you remember, we have done it in the concept that Lorentz actually wanted to see what happens if a current carrying conductor is placed in a magnetic field. He just wanted to see that is it possible to produce a magnetic field using a current carrying conductor. So this was the whole setup that was being used by Lorentz. So if you see here, there is a U-shaped magnet, that is horseshoe magnet. We have fixed it up here, right? So this is a battery. We have a positive terminal here and negative terminal here. This is a key to complete the circuit, right? So this acts as a switch to switch on or off the current, right? And these are the connecting wires. So here we have attached a conductor. Conductor is a wire actually, right? So conductor is it's hanged this way so that you are able to see the movement of the current carrying conductor, right? So what was the experiment of Lorentz for? What he wanted to find out from this experiment, as I already told you, he wanted to see what happens when a current carrying conductor is placed in a magnetic field. Fine. So let's see what happened. I'm just going to close the circuit, that is I'm going to just pass the current through it. Can you see? Can you see the movement? Right? See here, nobody is touching the conductor, this wire, nobody is touching. And it's slowly and slowly coming to halt, if you can see. But the moment I switch on the circuit, I close the circuit, I mean to say. You can see a jerk in that current carrying conductor. How come it's current carrying conductor? Because the moment I will close the key, current will start flowing through it, right? And if you see here, a jerk is there in the current carrying conductor, right? The moment I switch it on, I think you can see swing is there in the current carrying conductor. So what actually is happening, and is it a particular setup we need to talk about, this current carrying conductor and a magnet? Yes. Actually, this happened only and only when the magnetic field and current carrying conductor are placed perpendicular to each other. So what happened, what he related, and what concept he talked about? He said that if this current carrying conductor is coming into motion, right, it means there must be some force acting on it, right? He actually related this experiment with Newton's first law of motion, that is law of inertia. So if you remember, in law of inertia, we have a body at rest will remain at rest and a body in motion will continue to move in the same direction with same velocity until and unless some external force is applied on it. So if you see here right now, this is at rest, right? And this is a particular setup, that is the current carrying conductor and the magnetic field, the magnet. They are kept like this. Now, the moment I close the circuit, as we discussed, it comes into motion. It means this particular setup, the inclination between the current carrying conductor and the magnet is such that the setup gives a jerk, or it provides a motion to the current carrying conductor, that it comes into motion. Or I can say this motion must be because of some force existing. And how it is existing? It is just because of the setup that we have done, that the magnetic field of the magnet and the current carrying magnet, they should be perpendicular to each other, right? So this was your Lorentz experiment, and he was succeeded in proving that there is some force, and he named it as Lorentz force. And he told that there is a force, that is Lorentz force, that comes into play when a current carrying conductor and magnetic field are produced, they are placed perpendicular to each other. So this was your Lorentz experiment. Fine. So let's work on the last experiment of the chapter, electromagnetism, and it is related to electromagnetic induction. So kids, Faraday was a scientist who actually wanted to just work opposite to that of Lorentz. Lorentz wanted to see that if something is going to happen when a current carrying conductor is placed in a magnetic field, but Faraday wanted to check whether something is going to happen, and something actually he wanted to see whether we are able to produce current from a magnetic field, right? So he started working on it, and the setup that he used was a simple galvanometer, these connecting wires, and a copper wire was there, fine. So what he wanted to prove, that when a magnetic field is existing, is it possible to produce current using that magnetic field? So like here I am taking a magnet, right? And this is, no source of current is here. If you check out, no cell or battery has been attached to the apparatus. The reason is because we wanted to see whether current can be produced using the magnetic field, right? And to check whether minute amount of current is flowing, and if it is existing, in which direction it is flowing. That's why we have connected it with galvanometer. This is the motive to connect it with galvanometer, since it gives you the direction of the current flowing in the circuit. So this is a strong magnet. What actually happened? He just Faraday actually just kept a magnet near the coil, right? And he found out there was no change in galvanometer. If you see here right now, there was no change in galvanometer. Then he started bringing it near, right? And the moment he brought it near, he actually saw that there was deflection in the galvanometer. So again he kept it near the coil. But again there was no deflection in the galvanometer. Then he thought that probably the previous distance was the perfect one, which could produce current in this circuit. But again there was no deflection in the galvanometer. So after continuously experimenting, he concluded that it was not actually the fixed place of the magnet that was inducing current. Now it was production of current was there. Current can be there only and only if there is going to be a potential difference existing in the circuit, right? And potential difference here is the he introduced that there must be an induced EMF in the circuit. That's why induced current was there, right? So what actually happened? He concluded that there should be a relative motion between the solenoid or this coil and the magnet. And if you see here, he started moving the magnet towards, and he started drifting it away. And when the process was start, he found out that there was a deflection that was quite visible. For other, you must have seen there was not a remarkable deflection in the galvanometer. It was not very noticeable. But now I will show you, like when he was working on it, can you see the magnet was made to pass through the solenoid very fast, and then there was continuous deflection in the galvanometer, and the moment the magnet is going to move fast in the coil or the solenoid, the deflection in the galvanometer is going to be quite fast. Can you see here? And why this deflection? Because current is produced. Why current is produced? Because there is an induced EMF in the circuit. And why induced EMF? Now if I just keep it here, you can see there is no deflection. Can you see? If I take it away, no deflection. If I bring it near, no deflection. If I bring it here, slight deflection, and then it comes to rest. Slight deflection, and then it comes to rest. But the moment I just make the movement of the magnet very fast with respect to the surrounding, with respect to the coil, the deflection in the galvanometer also become fast. So that is what Faraday explained, that it was the change in the magnetic field per unit area, or I can say the magnetic flux. Because of the magnetic flux, there was induced EMF in the circuit, and because of the induced EMF, there was induced current in the circuit, that you can see in the galvanometer as well. So again he experimented on the number of turns. Like here the number of turns are less. If we increase the number of turns, then the deflection in the galvanometer, it will also increase. Okay, let's see. He just experimented again that if we changed, you must have seen when we were making it deflect, it was deflecting towards my right hand side. But if I change the terminals, is the deflection going to change? Let's see. If I change the deflection at the, the terminals at the two ends, is the deflection going to change? Right now probably the correction has gone weak. But when you so when he changed the terminals, he saw that the deflection in the galvanometer was in opposite direction, and when he increased the number of loops, increased the number of turns, there was increase in the deflection of the galvanometer. So this is how Faraday worked on the experiment that current can be induced with the help of magnetic flux, right? So this was again an important experiment, and on this concept only, on this principle only, our AC generator is worked.